Okay, good morning, everyone. Welcome to today's session. We'll start this morning with Miłosz Panfil, who will talk about non-integrability dynamics and integrability in interbreaking. Thank you, and please go ahead.
And good morning. Can you hear me? I guess it's working. Okay. So let me start with thanking the organizers for organizing this very nice event, and also let me thank for giving me some time to tell you about our research. So what I'm going to talk about is it's kind of in the title. So I'll be talking about non-equilibrium dynamics in quantum systems, and I'm interested in understanding how we can kind of use integrability to learn about it, and maybe move a bit beyond it by understanding what's happening when we break it. So this is a line of research that I've been collaborating with a number of people from our group in Warsaw, with Jacopo De Nardis, Leonardo Biaghetti from Paris, Robert Konik from Brookhaven, Jakub Pawłowski, Jacek Herberg, and Marcin Jerzejewski from the other university, on the other side of the city center of Wrocław, and with Sarang Gopalakrishnan from the Penn State. So I'm coming from essentially condensed matter quantum integrability. So idea of my talk is a bit, I know that you as an audience are a bit far from what I'm going to say. So I try to be kind of pedagogical and qualitative. I invite you to interrupt me, ask questions, and have the discussion during the talk. So let me start with a bit orienting ourselves. So when I'm talking about quantum integrability, what I really mean is kind of Bethe-Ansatz, Young, Baxter, R-matrix situation, and this can find applications in various context in physics. So today I will exclusively focus on this 1+1 dimensional many-body problems and applications there. Now, specifically, if we kind of zoom in there, we still have a number of choices. We could think about different physical realizations of the systems. So you could have integrable QFTs, you can have lattice models. So instead, today I will focus on essentially on integrable gases or liquids, however you want to talk it, however you want to call them. The idea is that we have a system which is defined in the continuum, and it has Galilean invariance. That's essentially that's essentially the setup. So now I want to explore how in quantum integrability in this very precise context can help us with understanding non-equilibrium dynamics. Okay. So what is non-equilibrium? So of course, there are many ways of bringing our systems out of the equilibrium. And there are many questions that we can try to answer. So here I kind of divided conceptually, at least in two categories of questions. So one is question of thermalization. So if I bring my system out of equilibrium, I want to understand how it gets back to the equilibrium, under what conditions, at what time scales, if it achieves some kind of stationary state, is this a thermal state or not, and again, under what conditions, about the interactions in my system, under what conditions on the initial states, etc., etc. So that's one class of problems. And another one is related to transport. And here I want to understand how, if there are some conserved charges and related densities, how they propagate through my system if I put some imbalance. Let's say I'm interested in the current of particles in a response to certain external forcing. And this transport can be of different natures, can be ballistic, diffusive. I can ask what determines maybe velocity or diffusion constant in terms of some underlying microscopic theories and things like this. And there are also some cases of anomalous transport. I will maybe talk about this at the very end. And we also want to find conditions where this transport is anomalous. Now, in all of the setups, it's kind of clear that interactions are important. That's what allows system to be brought back to equilibrium. That's what determines that diffusion, for example, is possible. So from this point of view, I want to think about integrability as a really kind of a tool which gives me non-perturbative control over the interactions. Okay, so I don't want to understand weak theories with weak interactions. I want to understand really what's the effect of interactions beyond some linear response theory and stuff like this. Okay, so so far so good. I will next slide will explain this. Yes, sorry, in 2 slides. So it turns out that there is a sorry. So now, without going into the details of microscopic theories describing the system of interest, we can do some certain phenomenological or qualitative studies. So if I think about systems reaching back the thermal equilibrium, I can assume that there's some temperature change because there is a heat current, and I can think about the presence of this heat currents, that it's because there is a gradient of temperature. So with this way, I can kind of close the equation and get the Fourier law for the equilibration, or for the Was it me? Okay. So on this kind of general basis, we can expect something like a Fourier law. And one of the aims of what I want to achieve is to understand how this constant here, this thermal conductivity, is related to some microscopic physics that I have. So in principle, I would like to compute this thermal conductivity from the first principles. By this, I mean confirming this equation and having a prediction for this number. Right. So more generally, we want to understand when this phenomenology breaks, or why it works, and what's the role of integrability in this thinking, whether we need to kind of correct for integrability or not, and things like this. So we have a kind of a universal theory explaining non-equilibrium dynamics, at least in classical systems, and it's a kinetic theory. Which comes essentially with 2 assumptions. So one is that matter is formed from particles, and therefore, if I think about gases, I can think that there is some distribution of particles with a certain position in space and time, and the distribution in velocities. Okay. So with this assumption, we can, or as Boltzmann did, we can write down the equation, which describes essentially 2 processes. So this distribution will evolve. So that's this term, the time derivative, because 2 things happen. I mean, particles have velocities, so they move from place to place. That's one thing. And then the other is this collision integral, which describes the effect of collisions with other particles, which locally redistribute the velocities. So this collision integral is essentially this kind of a master equation. We look at processes where, if I want to know how the distribution of particles with velocity v changes, I should look at the processes which, as a product, have a particle with velocity v, and subtract the processes which take the velocity v and scatter it to some other values. Okay, so that's essentially the logic behind the Boltzmann equation. From the kind of collision point of view, and this is from the point of view of this distribution. So we have to take particle from somewhere in the distribution, I mean the velocity from somewhere, and put it somewhere else, etc. Okay. Now the main assumption of this Boltzmann equation is the following: that after the collision, these 2 velocities quickly become uncorrelated, okay? Which is true in many cases, but false in some other cases. But this goes under this molecular chaos hypothesis. So the Boltzmann equation, or the kinetic theory, is quite successful. We can prove or understand many things. So, for example, this kind of standard picture that we can derive from it is the following. Well, when I have interactions, these interactions will lead to the collision integral. This will cause particles to scatter, And since they scatter, the resulting dynamics will be diffusive. So by diffusive, in the contrast to ballistic, I mean that the distance the particle travels is proportional to the square root of the elapsed time. Now, this is the kind of a standard picture, and it works well, at least in higher dimensions and sometimes in lower. But the lower dimensionalities have their own peculiarities. And these peculiarities are the following. First of all, we have something that's called the kinetic blockade. So in the standard situations, when two particles collide because of the momentum and energy conservation, they cannot change. I mean, the set of initial and final velocities are the same. So this doesn't lead to any redistribution of momenta, and therefore we cannot, the system will not thermalize. Okay? That's one thing. Now, another thing is that we might have integrable interactions. So we might have higher order processes or n-body processes, and they also are not very efficient at redistributing momenta. And the final effect, which is also important in 1+1 dimension, is this memory effect. So this goes against this Boltzmann assumption about the molecular chaos, that we have large chances for recollisions. So if this particle, so let's look at this horizontal arrow. So there is some particle moving, so it collides with this particle. As an effect of this collision, this particle has some velocity v. And then this particle collides with another with velocity v prime. But this v and v prime are not correlated because they just collided. Okay, so this is the kind of memory effect, and it's actually very difficult to consistently take those into account in the kinetic theory. So that's the, yeah, sure.
Change dramatically, so you can safely ignore it somehow if you are in 3D.
Yeah, so the usual logic would be that it's a dilute gas, and then it's very unlikely that you will recollide or like this, yes. But in lower dimensions, already in the 2 dimensions, it's quite problematic, and there are some ways of regularizing, some loop corrections and things like this that were heavily developed in 60s and 70s. Okay? Okay, so what instead I'd like to talk about today is in this 1+1 dimensional situation, where the effective picture that emerges is the following. So if I look at the purely integrable theory, so there's this denoted by this spiky interactions here. Then in integrable, so one way of thinking about the integrable theory, that the effect of it is that essentially we have a new set of nice quasi-particles that are kind of dressed particles by the presence of interactions, but interactions are quite peculiar in such sense that these effective new quasi-particles don't scatter. And therefore, in integrable theories, we expect the ballistic dynamics. So by ballistic, I mean that the distance is proportional to the time. Now, so that's what we expect in the purely integrable theory, or that's what we find in the pure integrable theory. Now, instead, if we break the integrability, so this is, we add to our potential some, sorry, so these 2 shapes could be the same, the blue ones, but we add to the blue ones something new, something that breaks integrability. I will tell more about this later. Then this introduces the scattering between these effective quasi-particles, because the theory is not anymore integrable, so the quasi-particles are not ultimate, kind of nice degrees of freedom. And this leads to diffusion and thermalization, etc. Right, so I mean, another way of thinking about this is that essentially in the pure integrable theories, we don't expect the full thermalization, but when we break the integrability, we will find it. So I will show some examples of this later. Okay, so the plan for today is I want to tell you a bit about. So this is kind of the first 2 points are background information, so to say. So I will tell you a few things about integrable systems and thermalization, or what we mean there. Then about inhomogeneous systems and their hydrodynamics. Then I will talk a bit about the Lieb-Liniger model. This is the microscopic model that we take, as a kind of as the microscopic model to describe these non-relativistic gases. And I will describe dynamics in these nearly integrable systems. I will decipher this GBB JKY, and I will also just mention probably some crossovers from Boltzmann to Navier-Stokes to KPZ physics. So this will become clearer later. So this is more or less the background information, and this is our contribution, from all the people that I've acknowledged in the beginning. Okay, so let me start. So I kind of oriented it around lessons. So the things that I have learned over those years. So it goes back to 20 years ago. So probably many of you have seen this. So this was a famous experiment in 2006 where they created a cloud of cold atomic gas, and they split the cloud in two pieces, and they let it evolve in this harmonic potential. Well, with an effect that the cloud was, the two clouds were passing each other a number of times, and therefore all the particles were colliding, etc. So why I'm mentioning this result is the following: is that when this cloud was kind of spread in three-dimensional cloud, then what they observed was what was expected is the fast thermalization, essentially kind of according to the kinetic theory of Boltzmann, you could understand it. Now, instead, if the cloud was really confined and one-dimensional, then they observed that the momentum distribution function was non-thermalizing. So that's what's shown here. It's not very visible, but the effect is that after tens or hundreds of collision, it was non-thermal. Whether in 3D experiments, it was thermal after a handful of oscillations. Okay, so there was certainly something that prohibits usual thermalization when we are confined to 1D. And the hypothesis or the explanation was that somehow with this experiment we are close to an integrable theory. In integrable theories we have a lot of conserved charges, and that's what prohibits us from the usual thermalization. So this was soon after kind of formalized in what we nowadays call the generalized Gibbs ensemble. So the story is the following. So if I take as my definition of quantum integrability, existence of an extensive number of local conserved charges, then those local conserved charges by definition they commute with Hamiltonian, and therefore they're conserved. So I just make a loop. And then if we think about statistical physics, what we should do is to try to maximize the entropy under the constraints. So now we have more constraints than usual, and therefore the resulting ensemble that we get is different. So usually we have just energy or maybe particle number and so on. And that's why we get Gibbs ensemble. Now we have all these charges, and therefore what we get is the generalized Gibbs ensemble with this coefficients beta here, which you can think about generalized temperatures. They just are kind of conjugate variables to this local conservation laws in the same way that temperature is conjugated to the energy in the usual setup. So this started in maybe 2008 with the work by Markus Rigol and his collaborators. But if in your free time, I invite you to read this work by James. I don't know, maybe some of you have seen this. This is the kind of, I think, a foundational paper of how we think about statistical mechanics nowadays from 50s, I think. And it's it's related to the information theory, which is kind of also becoming very popular and hot topic nowadays in modern physics. So it's nice to read someone's perspective on those from 60 or 70 years ago. I think it's a great paper. Okay. So in this experiment, they've seen something unusual. And then there were later experiments which actually shown that, this maybe we can skip, that actually shown that this generalized Gibbs ensemble idea works. So you can prepare your initial state, set up the ensemble, compute the compute these generalized temperatures, and then do some non-equilibrium dynamics here with cold atoms in both cases, and then you will find agreement with GGE. I mean, I don't want to go through the details of what's shown here. This is just some, kind of proof based on the, I don't know, on the authority. I mean, there are papers that show this, so we can discuss the details, but I don't want to do this. But the lesson is that this GGE works. So if you can make an experiment which describes integrable model with, kind of enough precision, the long time dynamics will go to this pre-thermal state described by the GGE. Okay. At later times, probably the imperfections of your experiment will make it thermalize to the standard GGE, to the standard Gibbs ensemble. But there is a large window of time where we can expect this integrable physics to reign the dynamics. Yeah, so this is okay. So this brings us to the question: what does it mean that system equilibrates, thermalizes? So I wanted to skip this. So, but the main assumption here is that we want to measure local observables. So if we don't measure local observables, the equilibration becomes more tricky. Okay, so that's lesson one. That if you have an integrable theory, it thermalizes or pre-thermalizes to GGE. Okay. Yes, so universal pre-thermal state of integrable dynamics. Okay, now let me move to another aspect, which is so essentially, I haven't maybe made it explicit, but what we are discussing regarded only homogeneous systems. At least this concept of GGE is kind of for homogeneous systems. Now, but it's interesting also to think what happens in systems which are inhomogeneous. So, just let me go back to this picture. So this is inherently inhomogeneous. This is in some external trap. There is a cloud. It's not homogeneous. The particles are not homogeneous in space. So if we are inhomogeneous, this brings us to hydrodynamics. And similarly, as we have a kind of Gibbs ensemble for conventional systems, we have conventional hydrodynamics, which takes into account the usual three conservation laws, which is kind of particle number, momentum, and energy. And it's built in the following way. So we have these three conservation laws. And now we assume that I have some inhomogeneous system, but it's not widely inhomogeneous. So if there is some different particle density, maybe from space to place, it's not that it's empty here and it's huge there. Okay. So you assume that this kind of smoothly changes in space. Such that essentially I can chop my system spatially into small boxes, and these small boxes I can assume that my system is homogeneous. Okay. So now the hydrodynamics is essentially about taking this thermodynamics of a small homogeneous system and gluing those systems together. And the conservation laws are telling us what will happen if something flows from one box to another. Okay. But each box is in its thermal equilibrium. It's just not in thermal equilibrium with its neighbors. So then to construct the hydrodynamics, we take those conservation laws and essentially compute. So so I wrote this here as really quantum operators. We can start with this, and we take some expectation value of those in an ensemble constructed in such a way that I have a product of thermal ensembles with varying temperatures and things like this. So in order to kind of close my equations, so I will have this expectation values of Q, expectation values of J, expectation values of Q determine my ensemble. So essentially I have to compute the expectation values of J given expectation values of Q. Okay, this is the logic of this hydrodynamic assumption. And this can be achieved by so-called hydrodynamic projections. So I don't want to go into details here, just want to say that, if you understand the thermodynamics of your system, you know how to evaluate expectation values of currents in a thermodynamic state, okay, in an equilibrium state. And this leads to these expressions. And in the end, with this expansion, we can close our equations and get the standard hydrodynamic equations. So that's written in maybe in unfamiliar language, but what we get here are just kind of Navier-Stokes equations for a fluid with this A and D. These are so these are essentially velocities, and these are transport coefficients. The first part describes reversible processes in time, and this one describes dissipation and some things like friction or viscosity, for example. Yes, yeah. So as you have to kind of assume that the boxes, the cells are uncorrelated. So so your range of interactions effectively shouldn't be larger than the inhomogeneity that you have in your system. Okay. So now all of this is, it's built on this conservation laws, and now here we have 3, but nothing stops us to repeat this when we have more conservation laws. So that's how we get to this generalized hydrodynamics. And the story is similar. I mean, essentially identical, just more conservation laws. So we also make this local equilibrium assumption. So we chop our system in fluid cells, and now in each fluid cell, we assume the system is not in a thermal equilibrium, but in the local generalized Gibbs ensemble. This generalized Gibbs ensemble is again specified by expectation values of all the charges that are present in our system. And therefore, if I want to compute expectation value of current, this has to be expressible by the expectation value of charges. So I can close my equations, and now I have an infinite set of equations to solve, which reflect all the conservation laws that I have in the system and describe, the fact that if the system is inhomogeneous, there will be flow of the related currents. So this has been also confirmed experimentally. Okay, and just simplify the notation to drop all those things, like expectation values and hats. So this has also been verified experimentally with cold atoms, and a bit more recent. So this is 2019, 2023. So this maybe I can discuss a bit more details. So this is an initial profile of a density in the gas. And there are some wiggling things and not so visible not wiggly things. So not wiggly thing is the theory, and the wiggly things are experiments, and we see that they're match perfectly. So here in the inset, maybe you can see here this dotted line. I don't know if it's visible. Not at all. Okay, so there is a line that does not match the experiment, and this is the line that you would obtain if you did the conventional hydro. Okay, so this shows that that they realize the system which is close enough to being integrable, such that the resulting dynamics is described by this generalized hydrodynamics, not by the conventional hydrodynamics. Okay, and this is another experiment showing essentially the same thing. So this is lesson 2. Okay. And then, the inhomogeneous integrable systems are described by the GHD. So this is continuity equation for all local charges. And as we will kind of explore a bit more in a second, we can think about the GHD equation as a collisionless Boltzmann equation. Okay. Are we okay for now? Okay, so now let me spend a couple of minutes introducing the Lieb-Liniger model. So this is a quantum integrable model of yes.
Hey, hydrodynamics, some of us, for instance, we think of the Navier-Stokes equation.
Yes.
Do you get some modified version?
Yes. So that's essentially the GHD equation is just a Navier-Stokes equation. I mean, it has a form of a Navier-Stokes equation in the following sense. It's well, it has second derivatives in x. So that's essentially what you expect from the Navier-Stokes like physics, right? That you have a reversible part, the Euler scale, and then there is dissipative part, which describes equilibration or homogenization. And now the point here is that so the stationary state of these equations won't be thermal equilibrium, will be GGE state. So what this equation achieves is brings your inhomogeneous state to a homogeneous GGE state. In the same way as if you have Navier-Stokes equation, you start with some inhomogeneous state and you will get thermal state in the end with homogeneous profiles. Okay. So let me start with describing the Lieb-Liniger model by talking a bit about the relation with these cold atom experiments. So with cold atoms, we can trap atoms in traps and therefore restricting their motion. So we are interested in trapping in this elongated shape such that effectively the dynamics there is one-dimensional. And well, one effect or one feature of the experiments is that usually you don't create single tube with gas, but many tubes, which are important for in certain scenarios because there might be interactions between the tubes, bringing us from the kind of purely one-dimensional dynamics to kind of quasi one-dimensional. I will show in a second how we can model those. So this Lieb-Liniger model, the kind of our Lieb-Liniger model is this one, is the integrable part. Which describes the kind of non-relativistic theory with short-range interactions and the usual kinetic term. And the interaction is ultra-local and parameterized by this constant C. Now, in reality, if you do experiments, there will be other terms that break the integrability. Okay? So that's part of the motivation to study dynamics of nearly integrable models is because those terms naturally appear in the experiments. So they're of different nature. So one is just inhomogeneity. So as I showed in this first Newton's cradle experiment, all those experiments are some external trap. Depending now on the nature of the atoms that are trapped here, we might also have some long-range interactions. For example, if the atoms have some dipole moment, there might be some long-range interactions within the tube and also between the tubes. Okay. So this all break the integrability, and we would like to understand what it means for the dynamics. Now, okay, just one slide of some technicalities of this Lieb-Liniger model. So it can be solved with the coordinate beta ansatz. So we can get standard beta equations with relations between quantum numbers and the quasi-momenta. And there is a thermodynamic beta ansatz description of it. So if we think about a large system, we don't want to think about the single rapidities or quasi-momenta. Rather, we think about their distribution. So I assume that many of you are familiar with thermodynamic beta ansatz, so I don't want to spend too much time on this. The one thing that I want to comment, though, is that we can make this thermodynamic beta ansatz describing states of both standard equilibrium, where the pseudo-energy in the Yang-Yang equation takes this form, this bare pseudo-energy. But we can also consider GGE, where we have this generalized temperatures, and then the contributions from different conserved charges. So here we have contribution from energy and particle number, which is lambda square and 1. And here we can have other contributions. So yes, so a few more things about the conserved charges. So as I said, we think about the local conserved charges. So there's some local density of them. And we know expectation values of those in this TBA state. So expectation value of this charge, it involves this distribution and the contribution from the charge, which takes this form. Now, what's important for us is that we will make an assumption, which is a bit restrictive, so it's not true generally, that this relation between QK and rho is invertible. Okay, so that's essentially saying that, if you have some distribution in statistics, you can infer it from its moments, essentially, which is not always true, but we will assume that it is the case. So we are working in this kind of this axiom that if we know the charges, we know the rho. Okay, so that's these two are equivalent, and this equivalence allows us to rewrite the GHD equations, which we formulated in terms of charges, as equations for this function rho. Okay.
In the case of non-homogeneous systems.
Yeah, so we're. Yeah, so okay, I can go back to this. So in the end, we assume that this each fluid cell. So I mean, we are looking at extensive charges, and we are assuming that each of these fluid cells is large enough to treat it essentially as kind of infinite system effectively. So we don't care about the corrections, if you wish to, from the finite size effect of this single fluid cell.
Density of charges that you said it does not depend on the size of the box.
No. Yes, that's true. Yes. So I'm always assuming that I have infinite number of charges, and I mean, I'm always assuming that I have infinite number of particles in each of my fluid cell, essentially. Okay. So these are two ways of looking at the GHD equations. So we can think about, as emerging from this large family of local conservation laws. So that's the left-hand side. On the other hand, we can think about them as an evolution equation for this density of rapidities specifying our state from the integrability. So these two are equivalent. Now, if we look at this one instead, this should resemble the kinetic theory of Boltzmann, okay? Because we have some distribution function, it evolves in time because there is something, the particles are flying from one plate to the other. There's an extra effect of diffusion, which is absent in the standard kinetic theory, and there is no collision integral here, okay? So this is so-called collision. I mean, the first two equations, the first two terms would describe something that's called collisionless Boltzmann equation. Now this is here corrected with this diffusion term. Okay, so now this kind of brings us, this observation, back to the kinetic theory way of thinking. So that's what I kind of hinted in the beginning. So if I have this quantum integrable theory, I specify my set by my state by the set of rapidities. Those are conserved by the Yang-Baxter equation, if you wish, in the evolution. Okay, so the lambdas are good labels for my eigenstates, so they don't evolve. So then now the only way to kind of bring life to them is by breaking the integrability. So that's the kind of idea. So therefore, if I have a homogeneous system, I can write down that my rapidity distribution or quasi-particle distribution will evolve in time because I let those quasi-particles from integrable theory actually scatter in a non-integrable way, okay? Not without Yang-Baxter equation. Okay. So we can do this in a homogeneous system, and we can also try to do this in an inhomogeneous system, therefore supplementing this GHD equation with the collision integral, okay? So that's our idea, what to do, and now we can essentially go into two directions. So we can discuss what are predictions of such theories, and we can also try to argue why this is the correct description and in what situations. So I will first talk a bit about the predictions. But maybe before I move there, I think it's a good moment to clarify something, if I can. Okay.
So, knowing for right that are
be stronger than you would get from the noise of the experimental setup, or are you trying to model the...
We try to model the experimental situation. Yeah. Okay, so now, so this picture doesn't answer the question, how do we add this? This is just some idea that we should put something to the right-hand side of these equations if we have non-integrable theory. Okay, so now let me show you some of the predictions of this. Maybe, okay, let me skip this for a second. We can get back to this if you have questions. So we considered various applications of this. So let me go through them. So we start with homogeneous systems to see the thermalization. Then we'll see what happens with the GHD equations if we break the integrability. And then this is more kind of entertainment, we look at some other applications coming from them or motivated by the kinetic theory. Okay, so the first thing that we wanted to understand is if I have these two cold gases, and let's assume that they're in a homogeneous state, but there is a coupling between them. So that's what happens in experiments. There might be some reciprocal interactions between the particles, and I can try to model this with this theory. So in this kind of phenomenological, if you wish, approach, I will just add here. So I have two gases, therefore I have two equations. And I will model or describe the collision integral that appears here by using the Fermi's golden rule. So I'm essentially assuming that this distribution here evolves because effectively this interaction introduces scattering processes or kind of non-zero matrix elements between different states. So this can be done. Not only kind of conceptually, but we actually know this matrix elements from the integrability. So that's a long history of computations in Bethe-Ansatz integrable models to get this kind of matrix elements or form factors. But now we can just use them as an input for the collision integral. So if I do this, and for simplicity, I will assume that my distributions ρ1 and ρ2 are the same. I can start with some initial state and I will have just some differential equation to solve, and I can solve this equation actually numerically and find the thermalization. So this is some initial profile in lambda in ρ of ρ, which resembles this Newton-Cradle experiments in the sense that this is like a cloud of atoms slightly split in two and divided. And if we start with something like this, after some appropriate time, it reaches the thermal equilibrium. So this is the final state here is thermal. It has a temperature. Now, if we consider different distributions, the thing become a bit more interesting even because then we can find some pre-thermal plateau. So there's some dynamics at shorter time scales, which is driven by this two-body effects. There's some ways of lift the kinetic blocking that I was mentioning before. So there's this drives this dynamics, but then ultimately the kind of three-body collisions, which are also responsible for thermalization here, will enter and the system will thermalize. Okay. So I don't want to spend too much time on this. This is just an illustration of that this can be made working, and it gives quantitative predictions. This is something more on this. Let me skip this. Now, for the inhomogeneous case, so in our tactic is to write down the GHD equation and again add this collision integral. So let's discuss essentially what's the physical picture. So the physical picture that we should think about this is the following. So we start with certain microscopic theory, and we have initially some inhomogeneous state. Okay. So if the state is not too inhomogeneous, what will happen initially is that locally it will equilibrate. Okay. So it's kind of before it realizes that it's inhomogeneous, it locally equilibrates. So this is the regime in which we have to be to make this work. Okay. Now, if it's an integrable theory, it will equilibrate to GGE. So let's assume that it did that. Okay. Now, since it's inhomogeneous, now these different GGEs will start to talk to each other, and the GHD equations will describe the flow of all those local conserved charges, or the evolution of the distribution function rho. And now at the last step, we kind of say actually, well, there's actually some weak integrability breaking. Okay, so now at even larger time scales, this integrability breaking term should become important. So this is the kind of qualitative picture of how we imagine this dynamic. So we start with some microscopic theory. At some times T GGE, it locally equilibrates. Then at times T GHD, it realizes that it's actually inhomogeneous and there will be flow of all these local conserved charges. And then at later time scales, it realizes that there is this integrability breaking term. What this integrability breaking term does, it kills all the higher conserved charges. So it kind of works as a filter for all these higher charges, such that we are left with the usual 3 conservation laws, and we should recover the Navier-Stokes equations. Okay. Now, so this is all very qualitative. Now, what can be done actually in practice, computationally, is that I can assume that these equations are true, and then kind of crank up some kinetic theory machinery to derive from this equation these equations, the Navier-Stokes equations. So let me just spend a second to discuss these Navier-Stokes equations. So in 1 + 1 dimensions, we have 3 continuity equations, for the particle number, for the one momentum, and for the energy. So the Navier-Stokes equations describe this, they contain, if you wish, this kind of non-universal terms, which is the dynamic pressure in the equation for the velocity, u, and heat current in the equation for the energy. So this dynamic pressure has 2 parts. It has a standard thermodynamic pressure, and there is a viscosity term, and the heat current contains the kind of non-universal number thermal conductivity. So our aim here is kind of start with these equations, derive Navier-Stokes equations, and compute these 2 transport coefficients. Mm-hmm.
Is there also a time scale where they locally realize that it's broken and those some example?
Yeah. Then, well, you would. So here we assume that this is that that the kind of effect of breaking integrability is the weakest among things happening. Yeah. So there's another direction. Mm-hmm.
Trying to the direction of the length direction to open.
Yes. Well, I mean, if you think about, of course, long-range interacting systems, then it becomes very, very different. I don't think at this stage I can really give some number or scaling to this, but yeah. I think it's still an open question, right, to formulate generalized hydrodynamics for long-range interacting integrable systems. So yeah. Okay, so now this can be done. This I can skip. So our result is that, well, first of all, we recover the Navier-Stokes equations from this GHD plus collision integral, and we can also compute this transport coefficient, viscosity and heat conductivity, and this I would like to spend 1 minute discussing because they reveal some interesting structure. So both of these transport coefficients have actually 2 non-negative contributions. So there are like 2. I mean, in a way, I mean, both of them are fine on its own, because for stability of thermal equilibrium, we know that these 2 coefficients should be positive. So there are 2 non-negative contributions which are of a different origin. So one is this diffusion term that's present in the GHD equations, and this is solely due to the presence of integrable interactions. And there is another term which comes from this collision integral and therefore from the interactions that break the integrability. So when you think about this at least to me it looks a bit like kind of we can start talking about universality classes, because now I can start with my integrable model and break integrability in various ways, and this will not modify this contribution to transport coefficients. It will only modify this one coming from the integrability breaking. So if I forget about this contribution, I can think about some universality class around my integrable system, and whatever I do, I can approximate my transport coefficients by this terms coming from the GHD diffusion. So this brings us also to kind of a question of modeling, which I will try to talk about a bit later. A comment is that if I do this kind of computations for a free theory, so I will take the most pathological integrable model, which is the free model, then these bounds actually become useless, because these coefficients are either infinite or zero. So somehow the presence of integrable interactions stabilizes the theory here. So this is the kind of a diagram that summarizes. So if I start with my model, I can identify the integrable part, and there will be contribution from it to the transport coefficients, and there will be contributions from the breaking of integrability. And the idea of universality is that sometimes maybe you can forget about the second part. Okay. Okay, so again, for this setup actually of two tubes coupled with this long-range interactions, if you wish, we can compute these things, and we can compute the transport coefficients. This is just to show that we find some expressions which are computable. Okay, and then the last example that I wanted to discuss is a case of a self-diffusion. So maybe I can just briefly mention it. So here we consider, so the self-diffusion is the kind of standard problem of kinetic theory, where I have two species of particles, and there is few particles of one species and a lot of another one, and I'm interested in the dynamics of this minority population. So you can think about this, that this particles of different kinds are in the same gas, so to say, or closer to what we do is maybe we can think about two gases which are coupled, and one is much more dense than the other, and therefore the dynamics of the dense gas is much slower than the dynamics of this dilute gas, and we can assume in the end that this dense gas does not evolve at all at the scales of the evolution of the dilute one. Anyway, so to keep the story short, now the important aspect is, because if you say that this gas does not evolve, but there is some energy transfer between the two gases, we are breaking energy and momentum conservation. So the only conserved quantity here is the number of particles, and if the only conserved quantity is the number of particles, you get diffusion equation. So here we find that in certain situations we don't get the usual diffusion equation, which would be just dt rho is dx squared rho. So this notation here is overcomplicated, but we get also a term, nonlinear term, which effectively we get the Berger's equation. So that's kind of an interesting story, that we have a certain setup with experimentally feasible to obtain Berger's equation from quantum physics. I'm mentioning this quantum physics here because essentially everything that I'm describing is kind of in a hidden way semi-classical, but actually this is one place where the quantum physics plays a role. So if I don't assume my particles here described by rho to follow quantum statistics, this term can be shown to be identically zero. So there is no Berger's equation in the setup for classical particles, but the quantum statistics makes this term possible. Okay. Okay, and in this case, we actually also run simulations with molecular dynamics to verify the theory, and it works. But this was for yeah. Okay, we can. If someone is interested, I can discuss the details. Okay, so this lesson 3 is that if we start with this GHD plus collision integral, we are effectively describing the nearly integrable systems, and with this we can understand thermalization, this prethermalization, emergence of Navier-Stokes equations, some process of self-diffusion. We also worked on something that's called relaxation time approximation. So sometimes you don't care about the details of your collision integral, but you can just capture some essence of it, and that's what the relaxation time approximation does. And it also enables some more analytic computations. But I don't want to discuss this any further. So let me move to the 4th lesson, which is essentially about deriving these equations. So we had this GHD equations plus collision integral. Can we derive those? Okay. So, so this maybe I can skip in the sake of time. And indeed, there is a way to derive this. And I would, this is not probably pedagogically the best choice to leave some derivation at the very end. But let me discuss this a bit, because I want to show you, I was kind of scratching the surface, so let's get a bit now into the details. So what do we do? So I have a theory, which, let me go back to the slide, which is some integrable Hamiltonian plus perturbation. Okay, so that's my Hamiltonian. And now I want to look at the evolution equation for the charges of the integrable theory. Okay. So this is, so for this local charge density, actually, I'm looking at. So we know what it is. It will be a commutator with the integrable part and the commutator with the interaction. So if I write my interaction as two-body interaction, I will get structure like this. And behind this equation, there is this integrable structure. So I know that these QIs are local charge densities for some local charges, and therefore they obey the continuity equations. And I can generalize this structure in the following way. So if I have an integrable theory, I have all these charges that commute with my Hamiltonian. Okay. But if I have a set of charges which are all commuting with themselves, it's a bit, I mean, what we call Hamiltonian is a choice. Okay, any of those charges could be a Hamiltonian. Okay, so we can be really egalitarian and consider the dynamics of this charge densities, or kind of conservation or continuity equations for dynamics not generated by Hamiltonian but by any other conserved charge. So this gives us this generalized currents Jij. So this is the current of charge J as when the charge Qi generates the time evolution. Okay. So there is this integrable structure, and now it probably doesn't take much to understand that much of the things that we can do in the usual setup in the quantum integrable models can be done also in this generalized one. Okay, because in the end, doesn't matter what is Hamiltonian, everyone commutes with everyone. Okay, for the structure. Okay, so then we find the equations like this, that this charge evolves because there is a current and there is the effect of the integrability breaking, which involves this generalized currents. And then similarly as before, we can kind of take an ensemble average of this expression, and we get equations. So we get a hierarchy of equations. So if I look at the one-point function, it will be due to this integrability breaking term coupled to two-point function. Now I can look at the evolution of two-point function. It will be coupled to other two-point functions and to three-point functions, and so on and so on. And so for those of you who are familiar with this BBJKY hierarchy of the kinetic theory, this is exactly the same concept. So we have a hierarchy of equations. And in principle, this is exact. Okay, this hierarchy is infinite and captures all the dynamics that we had. Of course, because it's infinite, it's impractical for computation, so we have to truncate it. And this is at this stage that we introduce certain approximations. So there are two kind of steps with which we introduce the approximation. So one is we truncate it, actually. And the other is that, as you see, that we have expectation value of charge, of a current, 2-point function of charge, current, charge, charge, current, charge, charge, current, charge, etc., etc. So I want to approximate all of those by expectation values and correlation functions of charges. So that's something that can be done thanks to the integrability and this assumption of local equilibrium. So I want formulas like this. That's essentially I express current charge as some combination of charge things. So with these two steps, I can close the hierarchy. So this is just a kind of equation that we in the end need to solve for homogeneous systems. So there is some simplification, but there is equation for 1-point function. Yeah, sorry for the two people in the back for the quality of the slide. But anyway, this is not important, the exact structure. What's important is that we have an equation for the 1-point function coupled to 2-point function, 2-point function coupled to 3-point function somewhere here. And then there is some equation for 3-point function, which is not coupled anymore to any higher correlation functions because we truncated the hierarchy and obtained a closed system of equations. So this closed system, I mean, it looks awful, and it is actually awful. But one can do certain analytic computations actually with this in the spirit of introducing certain approximations which result in sometimes this approach is called Markovianization. We can integrate out the correlations from this hierarchy. The assumption is that correlations evolve at much faster timescales than the 1-point function, and therefore for the evolution of correlations, we can assume that the 1-point function is constant. And this is what we do. This breaks time reversibility and leads to this GHD Boltzmann equation in a homogeneous system with the collision integrals. And these collision integrals here are the same as we were using from the Fermi's golden rule. Okay? I mean, we derived them to be the same as from the Fermi's golden rule. So that's quite an important result in this aspect. Okay. So what do we have? So we have verified this for some molecular dynamics of classical hard rods, and it's not so important. But we also verified it for experiments with dipolar quantum gases. So this is this Newton's cradle experiment that I've shown in the beginning, but now particles have also dipoles, and therefore they interact. And this interaction breaks integrability. And the strength of this interaction, because it depends on how the dipoles are oriented with respect to each other, can be tuned experimentally. So these are this blue line and blue shade. The red points are the experimental measurements of a thermalization rate, depending on the strength of integrability breaking, one way or the other. And the blue line with blue shade are our theoretical predictions. So you see that it works very well, I would say, given also a lot of uncertainties about actual experimental setup in the sense of what's really the initial state and things like this. Right. Okay, so for this probably I don't have time. So let me summarize. So we have now this generalized BBJKY hierarchy, with which we can derive this GHD Boltzmann equation. I think I started a bit later, no? And one thing that, despite that, I will not have time to mention is that, but I mean, you've seen this, we have also equations for correlations, okay? So this brings us above the kind of standard kinetic picture when we think about only the distribution function, and also how the things are correlated. And this is something that I mentioned at the very beginning. I mean, this will be, okay, I mean, this will be a journey. This one. Okay, so these memory effects are correlations between particles. And now we can keep track of those. So we can do better than the standard kinetic theory. And this is important. Why? Let's travel again. This is important for the following reason. So in 1+1D, actually, I was presenting a bit simplified picture of what's happening in 1+1 dimension at the level of hydrodynamics. So it turns out that hydrodynamics in 1D is anomalous, which means that at the largest space-time scales, actually the physics is not described by the Navier-Stokes equation, by the kind of a KPZ or super diffusive behavior. So this can be shown more or less rigorously, that if I start with Navier-Stokes equations and add noise, so noise, if you wish, kind of simulates the degrees of freedom that I have hidden under the carpet by going from microscopic theory to effective theory. I will get the KPZ universality class, which means that essentially correlations take over fluctuations. Things like linear response or Green-Kubo formula don't really work because we have some very slowly decaying so-called hydrodynamic tails. Now, the result of our work is that actually being close to an integrable theory stabilizes this Navier-Stokes equations. So what I mean is that we can, and this we have shown that if we break this integrability, so I start with some, so this is the length scale, okay? L is the length scale. So at the shortest long scales, I have this non-universal microscopic dynamics, which I haven't touched at all today, okay? Now at larger length scales, with respect to this integrability breaking perturbation, lambda, I will have GHD. Then at larger time scales, the Navier-Stokes equations will kick in, and only at even larger scales, this KPZ physics will appear. So this is something that we are working on now. I mean, it's actually very difficult to find a model in which you can describe the dynamics, along all those time scales to see all these crossovers. So this is quite challenging, but we might, we have some preliminary results, which would allow us to, to kind of see exactly this picture, not on the, with some numbers and at the quantitative level. Okay, with this, I suppose I should finish. So let me just reiterate this 4th and 5th in the progress lessons. So, the integrable systems, they do thermalize to the GGE. Now we have GHD to describe the dynamics if the system is in homogeneous state. If you break the integrability, then we know what to do. We essentially do kind of kinetic theory based on the GHD equation. And this all gives us information about thermalization, prethermalization, different phenomena, emergence of Navier-Stokes equations. And so, but on the other hand, it works only at the level of the one-body function of the density distribution itself. If you want to know about the correlations, we have also a formalist, which is this generalized BBJKY hierarchy, which allows to track the correlations and also derive these equations from more fundamental theory. And I think the ultimate application of this would be to understand this crossover from different regimes that we observe in the dynamics of inhomogeneous systems. And with this, I would like to thank you.
So thank you for the nice talk. Questions?
Yeah, thanks, Miłosz. So this final hierarchy derivation that you did, can you do this even for particles with spin? For like a lot of the stuff you've been doing is kind of scalar particles, right?
Yes.
But can you do this for spin as well?
I think so. Yeah, no, I mean, in principle, there is nothing. So there's GHD is known for spinful particles, and then everything could be repeated in that case. It gets more complicated because the TBA is more complicated.
Of course, yeah.
So I haven't discussed too many technical details, but what we rely here on is the structure of TBA to a large extent. So the more complicated thermodynamic beta ansatz is for your theory, the more complicated all of this will be.
So in such systems, as you mentioned at the end, that they have scale-dependent dynamics, can you describe them as uniform fashion across the scales? And in particular, can you study the spectral dimension of such systems?
Yeah, so I think we can with this. I mean, at least, so we believe that there is a universal framework which describes all these three regimes, and these are essentially these equations, and they should be able to capture all those three regimes. But this is in progress. I mean, understanding how this emerges from the structure of these equations, it's challenging, and we also want to have really some maybe simulation, molecular dynamics, or some sort of simulations that would show us this. And on the side of molecular simulations, it's actually also very challenging to have to kind of follow dynamics on a very different short and large time scales. So that's yeah.
Thank you. Is there some notion of viscosity here? Yeah, that's one question. Depending on the answer, I might have an.
Yeah. So I mean, so the simplest place to see the viscosity is this. So this is the viscosity coefficient in the Navier-Stokes equations.
Okay, that brings me to the question. Can you develop a boundary layer theory in this kind of business?
I'm not sure. I don't know. I mean, this would mean that you have a 2D system, and then along the one-dimensional boundary, there is yeah. I don't know.
Thank you.
Are these generalized hydrodynamic equations? So they have some integrability properties in themselves. I sort of remember something of the sort from colleagues in Oxford, but I don't know what the story is there. I have the image of a dispersionless.
Yes, so in that sense, there's still. Let me just display something. So maybe here. So indeed, I mean, they still conserve. I mean, they don't really break the integrable conservation laws. So in the sense, what does it mean? It means that the following. So if I take it's also to be practical, I take my initial state. It can be inhomogeneous. I compute total charges, all of them that are present in integrable theory. And those things will become, will be constants of motion of the GHD equations. So what we'll get in the end is a homogeneous state with exactly those conserved charges values.
There's a mass pair and so on.
This, I don't know. I mean, these equations, these equations are very complicated. So I haven't shown the details, but, in order to compute V and D, you need to solve some nonlinear integral equations in terms of rho. So how to...
Thanks for a nice talk. So in these comparisons with experiments, I suppose these systems are in finite volume. Was it important in any case in the theory that you had like boundary effects?
No.
So
we didn't go that far with modeling those. So it's no. So this is the theory here is for infinite system.
Okay. If there are no further questions, let's thank Miłosz again.
Thank you.
And we